The relationship between work and energy using kinetic energy and the work energy principle. Remember that energy is probably one of our most crucial strategies for problem solving for scientific processes. But energy itself is not observable, not directly measurable, not something that you can touch or hold or it's not tangible in any way, and there's actually a struggle to find a universally working definition for energy. It's just a quantity that we can calculate that we know is conserved. While we can't come up with a universal definition for energy, we can define different types of energy in a much better way. For example, we can define translational kinetic energy, and we can define some types of potential energy, and we can do that with full, concise equations and descriptors that make them easy to apply and solve for. One of the most crucial points when it comes to energy is something that I am going to continuously harp on, and that is that the sum of all types of energy will equal the total energy. So that means if you have more than one type of energy, in order to apply the law of conservation of energy, you need to find the total of all of those different types of energy. And that sum of all of the energies is always going to be the same. So if you have a system, you should always be able to calculate all of the energies, and as soon as you have your number, that number should be the same number every single time you calculate it, no matter what's happened. If the number changed, you need to figure out where that amount either came from or went to, because this is a conserved quantity. Energy is conserved, so that means that the number that you calculate should be the same, and you should know where each piece that made up that total ended up at the beginning and the end of a process, and you're going to be able to describe it. So let's go ahead and recall our current working definition of energy, which is the ability to do work. And let's also recall that that's not a total and complete working definition for energy, but it's going to work just fine for the mechanical energy that we're going to be focusing on. So even though I have this working definition of energy and you're using this working definition of energy, you know that this definition of energy is not the perfect definition of energy that you can use for all situations. But it's a great definition because the ability to do work does connect the idea of work and kinetic energy. If you have kinetic energy, you have the ability to do some work. It doesn't mean that if you have kinetic energy, you're working right now, though. It's just a matter of being able to do work with that energy. So let's go ahead and let's dive right into kinetic energy. All right. Any object that has motion has the ability to do work, and that means that it also has energy related to its motion. We call that energy related to the object's motion and related to its ability to do work kinetic energy. Kinetic energy is the term we use for the energy of movement. It's the ability to do work because of movement. So if something is moving, it can do work. Recall that if you find yourself encountering a moving bus, and that moving bus hits you, it will apply a force over some distance, so it will do work on you, and its ability to do work has to do with the fact that it's moving. If you stand in front of a parked bus, you can stand there all day, and that parked bus is not going to do work on you until it's moving. So let's go ahead and review some of our dynamics concepts, because the big connection that we used to start thinking about work and energy is the relationship of work and forces. So we know that in order for an object to accelerate, whether it's a positive acceleration or a negative acceleration, if we want to change the velocity from one number in magnitude v1 to another at v2, we're going to need a net force to cause that acceleration. And now we can use that net acceleration to do some net work as long as there's a displacement. So we can calculate the work done by a net force. We know we need a net force to change an object's motion, and we know an object's motion is related to its ability to do work. We know that Newton's second law says that the acceleration caused by a net force will be proportional to the mass. So F equals ma. And so that means we can substitute the ma for the F in the net work equation and say that the net work, instead of equaling net force times displacement, net work equals mass times the acceleration that the object experiences times the displacement. So it's the same equation with substitution. Moving further, we know from our kinematic relationships, so it's not that I expect you to have this number memorized, it's just that this number exists. This equation right here is actually, I'll show you, it's v squared equals v naught squared minus 2ad or plus 2ad. And if we rearrange this equation and we solve it for acceleration, we get this value right here. So since we know that acceleration from our kinematic equations is proportional to the difference of the velocity squared divided by 2 times the displacement, we can now plug that value in for the acceleration right here, just like we plugged in ma for the force up here. And then our network equation looks like this. Network equals the force, which is mass times acceleration, where this value is substituted for acceleration, times the displacement. Now that we have this, it definitely looks like we can clean it up. The first thing I want to do is I want to cancel out the displacements, and then I get that network, sorry, my net was awful, my network equals mass times v2 squared minus v1 squared all over 2. And what I'm going to do now is I'm going to simplify it and I'm going to distribute. I'm going to distribute the mass in. And so I'm going to say that the network is equal to the mass times v2 squared over 2 minus the mass times v1 squared over 2. And now this is my equation for network. If I pull out the divided by 2 and I just make it 1/2 m, then it's going to be that the network equals 1/2 mv2 squared minus 1/2 mv1 squared. And that's just a convention of writing out the equation. So our final answer is the network is equal to the difference between 1/2 mass times the final velocity squared minus 1/2 times the mass times the initial velocity squared. So if we take this value right here and we give it its own name, it's a quantity, and it's a quantity that we could find for any moving object with mass, and we're going to call that quantity 1/2 mv squared, we're going to call it translational kinetic energy. So that's 1/2 mv squared's new definition. It's translational or linear kinetic energy. So now we can write this value, 1/2 mv squared, is equal to the kinetic energy of an object. So now if I ask how much kinetic energy does an object have, all you need to know is its velocity, its mass, and you can solve for the total kinetic energy of the object, and you'll give me an actual numerical value. And it's a pretty simple equation, and just like work, it's a vectorless quantity, so it's scalar. So a positive would mean you added that amount of kinetic energy, and negative would mean you removed that amount of kinetic energy. And otherwise, if we're just talking about the kinetic energy that something has, it's an absolute value. This is the kinetic energy that the object has. I want to be very specific, even though we have only considered translational motion up to this point in time, that this is a translational energy equation. So that means that this only works for displacement in one direction. Whatever direction that vector is, it only works in that one direction. If that object is turning or moving in any sort of a circle, then we would have to use rotational kinetic energy, which we are not going to learn until chapter 9, I believe. Maybe chapter 8, I forget. So here I've defined kinetic energy, And so now every time I write kinetic energy into an equation, I mean 1/2 mv squared. So I can replace that and say that the net work is equal to the final kinetic energy minus the initial kinetic energy of the situation. And you know that final minus initial, or second position minus first position, is equal to the change in kinetic energy. So that means that the net work done on any object is equal to the change in kinetic energy that that object experiences. This is the work energy principle. The work energy principle is shown by an expression in this. What it means, which is just as important as understanding the calculations that can be done, is that the net work done on any object is equal to the change in its kinetic energy. So if the kinetic energy changes, work had to be done to change it. And the amount that the kinetic energy changed is going to be equal to the amount of work that was done. It's important to consider, in the previous unit, in the previous section, we could solve for the work done by individual forces, and we could solve for the work done by individual forces. But Newton's second law only applies to the net force of an object. The net force of an object is proportional to its acceleration. So that means that the work energy principle only applies to the net work of done on an object, because only net work equals net force times displacement. So we're only going to be using this principle to determine the net work, or the total work done on a system, never for the work done by an individual force. It is the work energy principle, and it tells us a couple of things. First of all, this is a direct relationship, so that means that if positive work was done, it means we increased the kinetic energy. If negative work was done, that means we decreased the kinetic energy. And that's pretty convenient to know, because that means if you speed an object up by doing work on it, you added work to the system to add energy into the system. If you slowed an object down by doing work on it, that means you removed work from the system, work was done on it, and the kinetic energy decreased. We can actually kind of consider this in a way that gives us a chance to look directly at the relationship between two different forces in a system. So here's a system where we're using a hammer on a nail, and at the point of impact, we create two forces. All right? One force is the force that drives the nail into the piece of wood. The other force is the reaction force, or the action pair force. It's the force in the opposite direction on the hammer. So taking a look, if we were going to consider the work done on the hammer and the work done on the nail, well, work equals FD cosine theta. And here, our displacement is we're driving the nail into the wood, and so we get that displacement. And here's the force that's on the hammer. And you can see clearly that that force is a full 180 degrees away from the displacement. So that means that the work on the hammer is equal to FD cosine 180. And we know that cosine of 180 is -1. So the work on the hammer is equal to negative FD. Here, when we consider the nail, the situation, what happened to the nail, we know that the force is in the forward direction, the same direction as the displacement. So that means that the work for the nail is equal to FD cosine of 0, and we know that cosine of 0 is 1. So that means the work on the nail equals a positive FD. A few things to consider is this is a force pair, so that means that those forces are equal in magnitude and opposite in direction. So, and the displacement that happens to the hammer is the exact same displacement that happens to the nail. So that means that the work done on the hammer was negative FD, so that's a negative work. The work done on the nail is a positive FD, so that's a positive work. Putting this into words, we know that the work that the hammer did on the nail is equal to the work that caused the hammer to slow down. When you hammer in a nail, the hammer slows down, so its kinetic energy decreases, which means that its change in kinetic energy is negative, so its work is negative. We've shown by looking at the dynamics of the situation that that absolutely makes sense. And we also know that since negative work was done on the hammer, that means that that hammer did that negative work, that hammer that had its work leaving the system, it went somewhere, it went into the nail, and it went into the nail, so that means that the hammer does positive work on the nail. That work, it's negative for the hammer, positive for the nail, same amount. That means that the energy that the hammer had went into the nail. The nail accelerates into the wood because it had work done on it that caused that force to be applied over that distance. So that means that the hammer slows down, the nail speeds up. Do they change velocities the same amount? Well, let's think about this. The work on the hammer is just the negative work on the nail. So you have positive work, nail, negative work, hammer, and they're the same value. It's going to be equal to the change in kinetic energy. The work on the hammer is going to be equal to the change in kinetic energy of the hammer. The work on the nail is going to be equal to the change in the kinetic energy of the nail. Kinetic energy is 1/2 mv squared for both of these. We know that for the nail, kinetic energy increased. For the hammer, kinetic energy decreased. And we know that those values have to be the same. They have to be equal. Well, we know that the hammer has a big mass, so 1/2 mv squared for the hammer, which is going to be a negative value when we calculate the change, is going to be equal to positive 1/2 the little mass of the nail times velocity squared. So this is now the relationship, and we know that since the hammer's mass is big and the nail's mass is small, a large mass, to get the same value from a velocity, you're going to have a smaller change in velocity. Whereas with a small mass, you're going to have a larger change in velocity for the nail. And this is why when a large object impacts a smaller object, the smaller object speeds up more than the larger object slows down. So if you didn't catch it, since work equals the change in kinetic energy, that must mean that work and kinetic energy have the same units. So that means that when you calculate work, right, work equals force times distance equals newtons times meters. Well, change in kinetic energy, or kinetic energy, is 1/2 mv squared. That's going to be kilograms times meters squared per seconds squared. If I factor out a meter, then 1 kilogram meter per second squared is equal to 1 newton. And then that meter that I factored out gets added in there. 1 newton meter is equal to 1 joule. So we can see that work and kinetic energy both are resolved to have the same unit of joules. When you're doing calculations like this, a lot of the times you're going to be considering the energy or the work of a system of objects, such as the hammer and nail that we just looked at. It's important to remember that when you're looking at the totals here, the total work, the total kinetic energies of the objects, you want to make sure that you know the total for the group or total for the system, and that means that you're just going to have to add up the sum of each of the individual objects. So if the change of the kinetic energy for the hammer was negative and the change of the kinetic energy for the nail was positive, and you wanted to know the change of the total energy in the system, well, positive kinetic energy and negative kinetic energy is going to equal 0 change in kinetic energy, which makes sense because the energy of the system is conserved. So let's take a look at a couple of simple calculations that you can do. The first one is we're going to look at the kinetic energy and work done on a baseball. It's a pretty straightforward example. Here we have a baseball of mass 145 grams. And it gets thrown, and as it gets thrown, the velocity causes the velocity that it's given is 25 meters per second. So if we wanted to know the velocity of the ball and the kinetic energy of the ball when it has a velocity of 25 meters per second, well, kinetic energy equals 1/2 mv squared. So when we plug in, we want to make sure we're plugging in with SI units. So that mass, which is 145 grams, gets changed to 0.145 kilograms. And then we can plug in 1/2 times 0.145 kilograms times the velocity squared. So it's going to be 25 meters per second squared. And resolving that answer is going to give us 45, two significant figures, 45 joules of kinetic energy. And the next thing that we want to take a look at is what was the work done. And to know what the work that is, we need to know what is the period that we're considering. And it says how much work has to be done to throw the ball from rest to 25 meters per second. So that means we're trying to figure out how much work it took to change the velocity from 0 to 25 meters per second. And here we use the work kinetic energy principle. So work equals the change in kinetic energy. So the work that we're trying to find is the final kinetic energy minus the initial kinetic energy. So the work is going to equal a final kinetic energy is when it's at 25 meters per second. We just solved for that. It's 45 joules minus 1/2 mv naught squared. Its initial velocity at the beginning was 0, and so 0 squared is 0 times 1/2 m is 0. So that means that the work done to cause the ball to move at 25 meters per second is equal to the change in its kinetic energy, so that means it's equal to 45 joules. So you can see that the work kinetic energy principle gives fairly straightforward problems to work out and fairly straightforward answers. Let's look at another situation, a situation in which the initial velocity is not 0. So taking a look at this situation, what we can see is we've got a car, Benny's driving it, so God help us all. The mass of the vehicle is 1,000 kilograms, and we want to know the kinetic energy change that would occur for Benny to increase the car's velocity from 20 meters per second to 30 meters per second. In other words, we want to know how much work does it take to change the velocity from 20 to 30 meters per second. We can use the work kinetic energy theorem. So that means that work is going to be equal to the change in kinetic energy. So if we find the kinetic energy difference, we will also know the work that Benny did by pressing on the accelerator, the work that came from the engine that changed the kinetic energy. So I use my definitions and I say the work is going to equal 1/2 mv squared minus 1/2 mv naught squared. In this problem, since the mass doesn't change, I might as well factor, and I might as well say that work is going to equal 1/2 m times v squared minus v naught squared. You don't have to do it that way. You can solve it any way you'd like. I just think that this is nice and clean and easy. So that means our work is going to equal 1/2 times 1,000 times 30 squared minus 20 squared. Plugging that in for values, 1/2 of 1,000 is 500 times 30 squared minus 20 squared. And I get that the work done on the vehicle is 2.5 times 10 to the 5th joules. So we changed the kinetic energy by 2.5 times 10 to the 5th joules. And that's how much work had to be done on the vehicle in order to accelerate it to 30 meters per second. And finally, the last example that we're going to take a look at is just a conceptual example, or looking at the relationship between all of the features of the work kinetic energy principle. So the question is, if you have a velocity of 60 kilometers per hour and you use the full force of the brakes to stop the car, that can be done in 20 meters. If, however, the velocity is double the initial velocity, what will the final distance be if you still apply the full force of your brakes? So this is going to actually cause you to think about the relationships that we have here, right? One of the intuitive answers that people give that's actually completely incorrect is they say, well, if you're going twice as fast, it must take you twice the distance to stop, and that's not going to be correct, and that has everything to do with the relationship between the velocity and the displacement. Remember, we're using the work kinetic energy theorem, so work is going to be equal to the change in kinetic energy. So that means that the relationship between distance and velocity is given by the definitions of work and the definitions of kinetic energy. Work is the force times the displacement. Kinetic energy, or change in kinetic energy, is the change in 1/2 mv f squared minus 1/2 mv naught squared. So even though it's a conceptual problem, I can conceptually use this equation and these relationships to figure out if the displacement really is going to be double or something much different. One of the things that you notice right away is that velocities are squared. So that means that it is not going to be a direct relationship between anything having to do with work and velocity. To simplify this equation, I'm going to say that the final velocity in both of the situations is 0, which makes the final kinetic energy in both of the situations 0. So that means we're just looking at the relationship between work given by force times displacement, and that's going to be equal to negative 1/2 the initial velocity squared times mass. So now, what happens if I double the initial velocity? What's going to happen to the distance if we assume that this force is constant? Well, if I double the velocity, that means that in that velocity area, I'm going to put in a 2 v naught, and I'm going to square it, and we're going to figure out what it's in relationship to. So that force stayed the same. What's happening to that distance there? If the velocity is doubled and we're squaring it, then that doubled, that 2 becomes a 4. So that means that the distance over here has to also increase by a 4. If the force didn't increase by 4, then that means that instead of having double the distance, we actually had 4 times the distance that it took us to stop at double the velocity. This is why speed limits are so important, and it's also why there's such a low velocity in residential areas and in school zones, because if you're speeding and all of a sudden that puppy or that kid chasing that ball runs out into the street, you're going to see them and you're going to try and stop, and if you're going too fast, it's going to take you too long to stop, and you're going to either have a flat puppy or a flat kid on the road behind you, which should make you feel bad about life.